Okay, guys, hopefully you had a good weekend. Um, just as a quick reminder, if you don't have your things turned in, please get them in by end of today. If you have labs that are not turned in, have not emailed to me, things like that, I prefer everything to get submitted via Moodle. I understand sometimes there's issues and it doesn't work. Please let me know if you are having those issues. A lot of times we'll just get it emailed. It's just easier to go back and forth on grading if everything's all in one place. So please use Moodle to turn in all the assignments. Make sure you have your quizzes completed. They will be required for passing grades, that kind of stuff. Also, with this week, we will start having tests. So at the end of the week, the test will unlock, and really it'll unlock as soon as you complete the quizzes. But the idea behind this is for the quizzes that you take, you need to get an 80% on them to have them marked as completed. If you have an 80%, you shouldn't have any problems with the test. Now, the test is going to be the previous week's material. So this week we're learning about series circuits and those types of things and the different configurations we can do with those and the different circuits that we can build. The test itself is going to be on last week's material. So kind of the lab safety, the opening parts of the class, understanding resistor color codes and understanding basic Ohm's law. So just kind of one device, 1 volt or one supply, currents, powers, that kind of stuff, and a lot of the terminology. So that's going to be the format for this week. The quizzes we'll have several in math. We're dealing primarily with fractions and manipulating fractions and converting them, things like that. And then, like I said, we'll dive into a lot more with the series circuits and getting things going that direction. Series circuits are a lot of fun. There's some pretty cool things you can make. One of the last things we're going to talk about is we're going to be building voltmeters. So I'm going to show you guys how you can build your own individual voltmeter, which then basically you can set it up to have a range of, you can measure on the same meter, you can measure between 2 volts, you can measure 200 volts, you can even measure 20,000 volts, depending on your application with the same setup, just a few different and additional components. So they're pretty cool. These can be used for all sorts of things. You can name anything, and really you want to know what your voltages are. At some points you're going to need to know, is my power fluctuating? Am I losing power? In the terms of robots, you need to have some sort of an indicator of how much power this robot has left, so you can quickly see it. Do I need to get it recharged? Do I need to fix it? Is there another problem that's going on? Is my batteries lasting as long as they should? That's another kind of consideration we have to make. So just keep that in mind. Like I said, with the quizzes, everything will be on Moodle, including the tests. Remember, it is open book, open note, but it is not open neighbor. Of course, now I don't have the internet. If you struggle with the internet, having the internet at home, we do have lots of internet set up at ISU. Okay, a lot of the parking lots have internet access to it. So obviously it's not the best situation, sitting in your car doing homework, but it is feasible. You can sit out on the grass in the quad. You can sit out here outside the building if you can't get in. But a lot of these buildings are open till late, and they do have opportunities for you to get in the internet. I know the Rendezvous has internet. The library is open if you need internet there. There's desks and tables and chairs and stuff set up there already spaced apart. There's computer labs on campus. So if you do need help with that, if you have problems with the internet, use one of those locations to kind of help with that. Also, let's see, and I think that's everything. Yeah, like I said, make sure you get your stuff in there. I'll work on getting your stuff graded. It should be done by this week. I usually get behind in lab books. It just happens. And that's one reason why I have you guys turn in PDF copies of everything. That way I'm not keeping your lab book for 2 weeks while I grade your reports. So if you don't see grades with those, just understand that. That's why I try to give you guys back instant feedback when I'm checking off and signing off everything. So if there's problems, you usually know about it and have a chance to fix them before you submit them for final grading. Any questions about that kind of stuff? Okay. So to get started, we're going to discuss. Oh, and then there was one other thing I forgot. At the end of the quizzes. So last week we had the report. This was that week's communication project. So this week and all future weeks, in the communication section, there is also another option that you need to do. And I believe you should be able to have at least started on the, it's called the muddiest moments. So what basically I want you to do is, this is an open forum for you guys. Basically kind of describe to me and to your classmates, what were some of the struggles you had this week? What topic did you struggle with? What was hard to understand? Because I guarantee you at some point, people are going to share your same struggles. This way you guys can help each other, you can build each other up and answer questions that you may have, just, with even, just some things, maybe you've gotten help with me several times, and sometimes somebody else explaining it will be the key that you need to unlock it. So the muddiest moments is just like that. It's a forum. Basically, write down a short paragraph, 3 to 5 sentences is really all I need, about what you struggled with, and maybe how did you overcome it, that kind of stuff. After you post yours, you also need to reply to 2 other students to get full points. So 70% of the score for this is your post, and then 15% is for each of your posts after that. Yes?
So will that be for like last week's work or for this week?
For basically everything up to that point.
Okay.
And then there'll be one for next week. So that'll cover from this week to next week, and then kind of go on. I didn't want to have 2 communication style writing projects in 1 week, so that's why last week we didn't do it. But this is something new this week that will continue on. And I do go through those, and I do read them, and I do take your guys' questions and considerations into mind, because if there's things that people are struggling with, I will try to adapt my teaching to make sure I at least cover that in a way that'll help you. So like I said, it's a way for you to kind of get additional help, feedback for me as far as the teaching style goes. Maybe I'm going too long on certain things, not long enough on others, that kind of stuff. I use those and I try to adapt to those as much as I can. So, questions? Okay. Okay, so today we're going to start talking about series circuits. Some of the things we're going to go through first is a lot of the different terminology. We're going to kind of get a little bit more in depth, a little more familiar with how some things are called. A lot of these you will see show up in the quiz. So pay attention to those, and understand a lot of what I'm teaching you is part of the quiz and things that we do want you to know. So keep that in mind. Okay, so one of the things we're talking about terminology-wise, we had this unit called a coulomb. Who remembers from last week what a coulomb is? Close. I mean, it does deal with what capacitors do. Anybody else remember what a coulomb was? It has to deal with charge. It's basically how much physical charge is there on a component. Now, the breakdown of this is 1 coulomb is equal to the number of electrons, or I guess I should say the number of coulombs, not 1 coulomb, but the number of coulombs is equal to the number of electrons divided by so basically it's the number of electrons that are present, because each electron has a negative charge, has some associated charge with it, and you need 3.25 times 10 to the 18th to get to that amount of charge. And then remember, we use the number of charge, and then we accelerate that charge with a voltage. That then turns into current. So it's the number of coulombs per second. So we have coulomb. We have a conductor. Now, for those musically inclined, it's not the guy that stands up in front and directs the band. Okay, so what would be a conductor? A metal, a wire, A material that has electrons that can move through it, because that's what we're trying to do, is we're trying to get electrons to move through a material. So a conductor okay? A conductor allows current to flow through it. Then usually, or not usually, the reason that it does this is they have an excess of electrons. Because if you guys have learned throughout your science classes, in the atom, the electron is trying, or the molecule is trying to become stable. And it becomes stable by having all of its shells of electrons filled up. And the way it does that is by sharing them with different bonds. But because they have all these electrons are moving around, some materials are easy to be able to kick the electrons free and pass them from molecule to molecule, atom to atom, versus other ones that have everything full. Because if you have everything that's full, it doesn't want to move. It wants to stay in that state. You can get it to move if you force enough voltage and give it enough energy, they can. So, but a conductor allows current to flow through it. It has excess electrons that can freely move. And it doesn't take a lot to knock those electrons out of their orbits. Okay? A constant current source or just a current source, as we kind of shorten it down to be. What do you think that is? A what? Yeah, something that flows the exact same amount of current at all times. So what this is, this gives us a constant current. It changes whatever it needs to do internally, voltage-wise. That'll change as needed as the load goes, but it'll give us a constant current. So in one application, that voltage on it might be 5 volts. In another application, that voltage might be 1 volt. Depending on what we have and what we have connected to it, it senses how much current it is, and it maintains itself at that current. A circuit breaker. What's a circuit breaker? Okay, not power. Current. I know, and a lot of times we use those synonymous, but I'm trying to get, make sure we get some of the more specific terminology in. A circuit breaker is a protection device that when there's too much current flowing through it, will open itself up to stop current flow. What are some of the common ratings for circuit breakers, like in a house? 20? How much? 15s? 60s, fairly less common. 10s and 100s. There are some variables like that, but usually what you'll see, and a lot of what you'll see, are these two guys right here, 20s and 15s. Most circuit breakers in your house are going to be a 20 or a 15 breaker. Coming into your house, you probably have a 200, a 250, or a 300 amp main breaker. So if at any time you're pulling more than 300 amps in your entire house, which if you are, you got something wrong or you're doing too much stuff at once. I've only ever seen those main breakers pop a couple times, and it was usually during lightning storms. If you've popped your main breaker, I hope you don't die. I'll just put it that way. Okay, a potentiometer, which is what you guys are starting to learn about now. Spelling is not my best suit, so I do apologize. That's why I have my cheat sheets. A potentiometer. What is a potentiometer? Variable resistor. Okay, and how these guys are physically built is, if you look at them, we've got 3 legs coming off of them. You can label them however you like, but this is how I like to look at them. So we have A, we have B, we have C. B is our wiper arm. That's the part that we can actually adjust. Around the outside of this guy is a great big resistor. Now, depending on what that resistor is, we'll tell you what the maximum voltage is. So that we label them as a 10K potentiometer, a 5K potentiometer, a 20 turn resistor, things like that. Those are the different names for them. And well, what happens is this wiper arm is going to be physically touching this resistor band somewhere. Anytime you measure from here to here, you're going to get the max resistance. Doesn't matter where that wiper arm is. When we measure from here to here, this is based on basically the percentage that you have it set at. And they're going to be, so the percentage of the whole, and then this is also, and then this is the rest. So if we have 50% on one side, how much do we have on the other? 50%. If we have 15% on one side, how much do we have on the other? 85. And the reason that that's important is when we look at it in terms of a schematic view, this is point A, this is point B, this is point C. So our wiper arm is going to be moving up and down and creating two separate resistors. So now we have RAB and we have RBC. And they're going to split up. One of the things that we can't do is this is a physical connection inside. We can't break that apart anywhere. So we can't get in and measure currents, but we can measure voltages. Now, why is this important? Well, there's going to be some circuits that you guys are going to design. You're going to have a signal coming through, and you're going to have something that's running. So let's say, like, instead of this voltmeter, we have a fan. So we can have this potentiometer set up so the more voltage it gets, the faster the fan is going to spin. So we can set it up as a control for, the speed of direction of our fan, whatever it may be. So as RAB gets larger, the voltage drop also gets larger. And then if we wanted to turn the fan down, we could turn it down so this becomes negligible. All the voltage will be dropping here, and then the fan's going to slow down and stop. So it's a way that we can use to control different devices. And it gives us two options right off the bat. Now, the other one that we're going to talk about is a rheostat. So a rheostat and a potentiometer, they are the same device, but we use them separately. The difference between a potentiometer and a rheostat is it looks like this. This is A, this is B, this is C. So what we're doing essentially is we are shorting out the portion of the resistor that we don't want to use. So instead of having two options, we only have one. We only use one. This is the true variable resistor. So now as we do this, we're only going to have one resistance value instead of splitting it up into a pair of them. This one in the rheostat, we have to be careful, because if we turn this down to where basically RA and B, or RA to B, is equal to 0, if we don't have another resistor in line, our current is going to spike, which is going to cause problems for you guys when you're measuring these components in the next lab or two. You're going to get, so as the resistance approaches 0, current is starting to go up towards infinity. And your meters cannot handle infinite current. They have a tendency to burn up and blow things up. Yep. So really the big difference is here is the variable resistor, the potentiometer. we use it to split the voltage up to where we always have this amount of resistance in the circuit. We just are using bits and pieces for different applications. A rheostat is the true variable resistor where we only have one, but we have to be careful when we get down into the 0 range because we can cause problems with our circuit. So usually what you'll see in this instance is you'll see another resistor. We'll call it a shunt resistor, for example. So that way there's always 100 ohms of resistance in the circuit. As we increase this, we're just going to increase the resistance total, give us less current things. But then as this approaches 0, we're not going to overload our current. Yes, Max?
So why would we put that resistor in there if we just can't short it out?
That's just the schematic symbol for shorting it out. But the idea is we're only using this portion. We don't care how much is there. We're just ignoring it, and it's not part of any of our calculations or equations. That's just the schematic symbol difference versus a rheostat and a potentiometer.
Okay.
And does it physically look like a potentiometer?
Oh yeah, they're the exact same device.
We're just not.
We're just not using part of it.
So it's attached to two leads instead of.
Correct. You would attach it on here to either A and B or B and C. So only use 2 out of the 3 legs. That's the biggest thing, the difference between them. Functionally, they are the same component. How we use them is just what makes them different. Questions about that? Okay, so the next thing that we need to talk about is series versus parallel. Now, I already brought up series and parallel when we're talking about the rheostat, but the main definition that we're going to look at is a series circuit. The biggest thing here is one current path. We're going to be talking about a lot of, when we look at these circuits and analyze them, are they connected in series or are they connected in parallel? Because depending on how they're hooked up, it's going to change how they function. So series is one current path. You can trace one loop from your battery all the way through everything back to the battery again, or back to whatever your voltage source is. Parallel has multiple current paths. So there will be some circuits that will be strictly series circuits. We'll have some circuits that are strictly parallel circuits. And then the week after that, we're going to be combining these two together. So we have series and parallel in the same circuit. And we have to analyze them just a little bit differently. But the whole idea is we're going to simplify everything down until it becomes a series circuit. That's the whole idea, is we'll take parallel and convert it all the way down into a single series circuit with one voltage supply, one resistance. Any questions about that? Okay.
So with the parallel system, since there's multiple paths to current, does that mean you're going to have higher current?
Yes. Yes. So one of the big differences, so like this is a series circuit. So we have 1K ohm, we have 10 volts. In this circuit, what's our current? 10 volts divided by 1,000. 1 milliamp. 10 milliamps. Moved one extra zero. So in this case, we have 10 milliamps. When we go into series, we go into parallel, we have our 10 volts. Our I total, the total current in this guy, becomes 20 milliamps, where these guys stay the same at 10 milliamps.
So will the current be like equally displaced between both the resistors? Or?
If they're equal.
Okay.
And we'll talk about this next week. I'm just giving you guys a kind of an example of the difference here. So the thing we can have the exact same components. We start throwing in parallel. This is what's going to be going on, and we'll talk about how that happens next week. This week we're focusing in just on the series guys. This is the next most important part of electronics. So the first part that we have is Ohm's law and Watt's law. Okay? With them, that gives us the functional fundamentals for how electronics works. Kirchhoff, he came along later and he found that everything in a circuit reacts with each other. So, and because we have the conservation of energy, we can't create or destroy energy, we can't have to create matter, things like that, we have to have a balance. So what Kirchhoff did is he came through and he came up with two current laws, or two laws. So the first one we're going to refer to as Kirchhoff's voltage law. So basically what this is saying is the voltage into a current, or into a circuit or a series or a system must equal basically voltage used. So voltage into a system must equal the voltage used or the voltage dropped. So the idea behind that is if we have three components in a circuit, in a simple series circuit, they're going to drop between the three of them the total voltage that goes into the system. We can't lose any, we can't gain any. They have to be balanced. If they're not, there's something wrong. Either an assumption we made is wrong or a calculation we made is wrong. This is one of your checks as you're doing these types of equations. Does the input match my output? Does my output, or what's being used, match what I'm putting into the system? Kirchhoff's law has to be satisfied. When we get into parallel and series parallel, it's a lot more difficult because now we have different ways we can go, but Kirchhoff will always work out, no matter what path we take. That's another way we can tell if we did something right. If we go one direction on a parallel circuit and we come up with an answer, we go another direction and we don't get the same answer, there's something wrong. So that's Kirchhoff's voltage law. His second law the KCL, which is his Kirchhoff's current law. And this one states current going into a node, which is basically a connection, must equal the current leaving that node. So basically what it's saying is if we have a circuit, it comes into here, we have two components like this. We come in, let's say we have 10 amps coming into this direction, coming down across these resistors, we have 8 amps going through here, we have to have 2 amps going out the other direction. So we've got 10 coming in, and we have 10 coming out. And they can split up whichever way they want. We can also look at that in a series circuit. So if we have 10 amps coming into here, we hit this node, which is a connection, so we have a wire that's connecting our voltage supply to our resistor, and then we go from the resistor coming out of this node, we have to have 10 amps. Once we get outside of the resistor, we hit another wire, which is another connection, which is also known as a node, means we have to have 10 amps. So with just Kirchhoff's current law, we see and we prove that in a series circuit, the current is going to be the same. Because it has to be. Think of all the different spots here as connections as well, if you need to do that for the current. Current going into a node must equal current going out of a node for Kirchhoff's current law. Kirchhoff's voltage law, the voltage going into a system has to equal the voltage being used or dropped coming out of a system. Any questions about that? Yes?
So, how does it work, like, if you lose that current, like, if you have like a current draw?
So your current drops somehow?
Yeah.
So like in this example?
Yeah.
So let's say this one burns up for some reason or whatever.
Yeah.
So if this guy burns up and is no longer in the circuit,
Is that like a short?
you could either have a short or an open. So if you had just a short, a wire that's going to bypass it, now you're going to have zero resistance. You're going to have 10 amps flowing this direction or more, depending on what else is in the circuit. Probably the more. And you're going to see the current spike and blow stuff up.
Okay, and then the second resistor doesn't have any.
Has none. It will have zero current flowing through it.
Because it takes the path of least resistance.
Takes the path of least resistance.
So basically, in order to control the current, you have to have resistors that will add up to the current that you are.
Mhm. Yeah. Yeah.
And that will determine the current all the way from the very beginning to the very end.
Yep.
Okay. So does it really matter where in your circuit you place your resistors then?
To a point, it will.
Okay.
And we'll be talking about that especially when we talk about series parallel, because it matters where they get put at that point, because they're gonna, like I said, they're gonna react differently with each other. Any other questions about Kirchhoff? So when we're working through these, remember Kirchhoff. Remember Kirchhoff. When you get through problems you may not understand, use Kirchhoff to start figuring it out. Usually there's enough clues in there to start at least getting a diagram of what's going on. We're going to be talking a lot about what's my Kirchhoff voltage loop doing, what's the currents doing, what's splitting up where, what's going where. And if we remember these two laws, we will be able to work through anything that we come across. Okay. One of the specific things we have in series circuits is we can have multiple batteries. Okay, so let's have, for example, I have two batteries in line with this, and actually let's change this. What is that schematic representing? A light switch, a flashlight. Okay? We've all got flashlights. We have a AA battery, and a AA battery, positive, negative, each is 1.5 volts. Okay? In this configuration, what's our net voltage? 3 volts. And how do we know that? We add them up because of their series and their polarities. Okay? Positive goes to negative, negative goes to positive. We make a complete loop where we connect them together. Our voltage total is equal to 3 volts. Okay? In this configuration, they are called series aiding. They are aiding each other. So we get two batteries and gives us the voltage that we need to be able to provide for our light. Yes? What? Yes, this is a switch. Yep, this is the schematic symbol for a switch.
So is that why like flashlights can work if only one battery is 100%?
Yes.
Or it won't work as
It won't be as bright. You won't have as much current, things like that. But yes, that's why they always say don't use a new battery and an old battery, because you think you're putting in 3 volts. Really, you're only getting 2 volts, 1.5 volts, things like that. It's not going to work. If there's any doubt, measure the batteries. The AA's, AAA's, those guys, C's, D's, if they start dropping below about 1.1 volt, they're pretty much starting to die, and they just really quickly ramp off as far as what they can actually produce. So in this case, we have series 8ing. What happens if we have the same circuit or the same flashlight, and we do this? They're going to cancel each other out. Why? Because the negative's pointing to the negative, and the positives are pointing to the positive. These guys are series opposing. Now,
Something like that, or is that just always going to be there?
yes, there is reasons to do that, because there's times where you're going to want to create biasing for a different part of your circuit. So if you want to be able to power your battery or power whatever it is with 2 different supplies, like you could have a 12 volt supply, you could have a 9 volt supply later on down the line, or even some backup AA's. You can have them in there. If you need a certain biasing, you can have one in an opposing bias, and then depending how everything interacts with each other, it might not be that big of a deal. But the biggest thing is to look. If they're series 8ing, they're going to add together. If they're series opposing, they're going to subtract from each other. And there will be times that when we get into the capacitor portion of this, you can basically charge up a capacitor to a certain voltage. That capacitor then acts like a battery. Depending on how you charged it up, now it's going to fall in one of these 2 categories. Is it going to be a series 8ing or series opposing? Because there are times where you don't want your voltage, once you charge the capacitor up, you want it to discharge and fight against whatever's charging it to decrease your voltage to kind of keep it regulated. It's a quick way to make kind of a voltage regulator, because where it'll oppose it and the voltage will never get over a certain amount. You open a floodgate, you open another one back here, it's going to hit, and so then the net force coming this direction is going to be a lot less. So you can use it for control methods. You're going to burn up your batteries faster if you do that. There's more efficient ways to do that, but you can, and depending on when you need it to. Huh? Yep, a quick and dirty method. But capacitors will do this whether you want them to or not. Intentionally, they're going to charge up, and then they're going to affect your circuit. So the idea is you got to understand if they're going to be 8ing or opposing to either add or subtract them. Now, in this example, let's say we had a 3 volt. Actually, let's have we'll stick with our batteries. We have a 9 volt and a 1.5 volt. What's the net voltage that we have on that circuit? 7.5. They're not going to completely cancel each other out. Whereas this one, we're going to get 3 volts. But if they were the same, they would completely cancel each other out. So that's why even if you do this, and if you have a battery, you put in a fresh one that's 1.5 and you put in a dead one that's like 0.3, you're still going to get a little bit of light, but it's not going to be as much as if you had that battery in by itself. So that's another way you can test your batteries, is you can flip them around and see, start comparing which one's got more of a voltage on them if you don't have a meter. Okay, any questions about that? Okay, so the next set of terminology we need to talk about is an open circuit, a short, and a short circuit. They all kind of represent the same thing, but the biggest difference is timing. An open circuit is a circuit or a portion of a circuit and minus. So an open circuit is a circuit or a portion of a circuit that has no connection to both a positive and negative potential, a positive voltage and ground. Sometimes this is by design. Sometimes we build it so that there is an open circuit until we're ready to connect something to it. That we're going to talk about at the end of this week's material is a voltmeter. We're going to design a circuit that part of the resistors, until we use them, is an open circuit, but it is by design. The difference being an open, this is a sudden change in resistance increasing ing to infinity. So an open circuit is something that we design into it to not have a connection till we want it. An open is a sudden change in resistance, basically increasing the resistance of something to infinity. So if something burns up, if we have a resistor that gets too hot and turns into this, we now have an open circuit. Because if you've noticed when you're doing your measurements in lab for resistance, if your probes are just sitting out in the air like this, what do they read? Like a 1. Basically it's saying there's too much resistance, I cannot measure it. If you get a powerful enough DMM or meter, you could put your probes apart and you could actually get a measurement between those two. You're looking in the realm of several hundred megaohms of resistance just in the air. And I think it's like, I can't remember the exact value, but it's like 100,000 meg per inch or something like that. So I can't remember if that's the exact value, but it's a crap ton of, so the farther you get apart, the more resistance you have. That's why, like when you see arcs and things like that, and sparks and shocks and static electricity, you can see it because you've now arced across those 2 points, and you're now forcing electricity to go through the air. It's kind of fun, especially when it's controlled. Yep, because you're pushing a ton of energy. And the electrons get rid of the energy by converting it to heat so they can drop back down into their stable platform. In the lab, I'll show you guys, we have a Jacob's ladder. That's basically what you're doing, because you're forcing electricity to jump through the air. And because of that heat, it then pushes up the next arc. So the sudden change in resistance, this can be caused not necessarily by things burning up, by things getting unplugged, by not having the right connection. And the reason it's a sudden change is because these ones usually will fight you in lab. You'll disconnect a resistor, you move things around, you'll tug on your probes or something like that, and it'll come up so they're no longer making connection. Now you have an open, which also means there is no current. However, when you have an open, you're going to have a voltage drop of everything on either side of it. So, for example, if you have a circuit here, everything's chugging along, you got 3 volts here, you got 3 volts here, you got 3 volts here, you're running some nice pretty LEDs, If one of these guys opens up, say for example that guy, we now have no current flow in the circuit, but if you were to hook up a voltmeter across it, you would see everything in that path that would be dropping. So you're dropping all the voltage over here, but you have no current flow. So if these were LEDs and you unplugged one of them, all of a sudden all of these guys would disappear. And they would, or not disappear, the light would go off. But if you took your DMM and plugged in the spot right where you took it out, you would read that whole 9 volts. There's no completion to the circuit. Your voltmeter actually completes the circuit, but it has a high enough resistance that you're not going to get any negligible current flow.
So is that like when if you were to cut it through the lights, it would glow on both sides?
Yep. And like connecting them together, things like that. So, yeah, so an open circuit, no current flow, you're going to have the voltage drop of everything in that path. That's going to come a little bit more relevant when we get into parallel circuits as far as the opens. But with this guy, you can go through and troubleshoot a circuit by measuring the different voltage drops. So if we went in here, we're like, okay, what's going on? We put our voltmeter across this guy. What's the voltage drop going to be there? 0, because there's no current. Yeah, because the circuit's open. So we're going to measure here, we're going to have 0 volts. We measure here, we're going to get 0 volts. We measure across this guy. So let's say we thought we had it plugged in, but on our breadboard, this one was plugged in on row 5, and we were supposed to be plugged in on row 6. Very easy to do. We missed it by one line on our breadboard. We're going to get this same situation. We're going to measure 0 volts, 0 volts, and across that guy, we're going to measure all 9. Because for all intents and purposes, these guys have become shorts. They're not even in the thing. They're not dropping any voltage. They're short. Or a piece of wire. Another way to think about it. 0 voltage drop means it's a piece of wire. Does that kind of make sense? Like I said, once we'll get into more with troubleshooting with this, and you'll start to see it and recognize it more. But for right now, does that at least have an inkling of, okay, I can at least accept that for now? Okay. Opens are not terribly bad. Most of the time, because you're not going to have any current flow, it's going to protect your circuit. You shouldn't be blowing fuses, things like that. Opens are pretty common, unless when we start getting into parallel circuits, opens start to become a little worse. So if opens aren't too bad for a series circuit, what do you think is worse? Shorts. Okay? So a short circuit is a bypass. Just plain and simple. Same if you think with open heart surgery. If somebody has a bypass, what do? They go in, they find where it's blocked in the heart, and they literally put in a new route for the blood to travel around the area that's blocked off. They bypass areas. Same with short circuits. There's going to be times where we want certain components to be shorted out. When we get into AC/DC circuits in the next 8-week class, there's going to be times that at certain frequencies we want resistors to act as a short or a capacitor or whatever. So it'll act as a short. You won't even see a resistor. It hides it. So we can use it. We can still have the circuit to set up controls for DC, but then the AC isn't even going to see it. It's not even going to be there. So there's times where we design these guys to be part of the system. We want it to short out at certain times, but we want it to do it in a controlled manner. So a short circuit is a bypass, an intentional bypass. A short is a sudden decrease in resistance going to 0. So if I have my circuit, and I have my resistor, we got 10 volts, we got 1K ohms. How much current did I have? 10 milliamps. So let's say I'm doing some work over top of the circuit. This could be running my motor underneath whatever I'm working on. This happened to me at work before. We were working on a board above us, trying to get some wires and things clipped in, and underneath of this was a control for a pump to keep water circulating through this tool to keep it from overheating while we're working on it. At some point, one of the wires, or a screwdriver, most commonly it's a screwdriver that falls, the screwdriver came and fell and landed here across the motor. We now created a short circuit, okay? So in this piece of metal, if you were to measure it, it's going to measure very, very little resistance, okay? Approaching zero. It jumps onto this. What does our current do? So as resistance decreases, current increases. Boom! Usually blew a circuit breaker. We probably have to get new tools because there's probably a chunk blown out of the tip here. There's probably a chunk blown out of the handle there. In this circuit, we were running 15 amps through the circuit before we hit it with a screwdriver. It's going to cause problems. Shorts destroy equipment.
So, is that basically blowing it out? Is that because it just got too, the atoms and stuff got too unstable and just
Too hot.
blew it out of there?
Too hot, yeah. They had so much energy, they were so excited that they expelled so much heat that they literally vaporized the metal that was touching it.
Wow.
And it happens like that.
No longer need a connection with the metal to keep their electron balance. It just departs.
Yep. Yep. And completely vaporized it. It heated up to the point instantly where the metal turned from a liquid, from a solid to a liquid to a gas. Instantly.
Wow. That's kind of terrifying.
So shorts are the most deadly thing to equipment and to people. Because if somebody was holding on to that thing when that shorted, now they're the connection that's going to go somewhere. Especially if you're wet. Like I was saying earlier, wet decreases your resistance. You now have 300 ohms of resistance versus this great big coil of wire that it's trying to push through, which is all a motor is. You're trying to push energy through coils. It's going to go through you. And that's the other thing you'll see is when people are reaching especially high power stuff, it's always one-handed. You never touch the equipment with a second pair of hands. Same. Yep. Because there was a lot of times you'd see people, and I kid you not, we would get into these implanters that, 10,000 volts to start them up, and then in the areas they range up to 200,000 volts. Okay, they have these. They literally are called this. They have this great big long stick about this big. It's fiberglass, has a metal hook on the end, has a copper wire about that big bolted to it, which runs down to the tool. It is literally called a chicken stick. You literally open the cabinets of this thing, and it has these great big capacitors that if they haven't discharged, and you grab that stick, and you touch the side of the tool to it. Sometimes it arcs and scares the crap out of you. But you do it in such a manner that it's going to be safe, and it safely discharges this voltage that may have built up. Because we had problems where we didn't have grounding wires, so that voltage charge didn't dissipate. It would slowly build up, and then we had to discharge it before we could get in there. The guys knew it was going to happen, made me do it, jumped out of my skin when it happened, and then they laughed. But they knew I was perfectly safe as long as I wasn't being stupid with it. But the first time I did that, I about died of a heart attack, and then the other guys were laughing. But that's all we're doing is we're shorting out the tool. We shorted it out to ground to discharge it to make it safe, so we could get in there and actually operate on the equipment. So there's times, like you said, where we had a short circuit. In this case, it was the bypass to discharge the electricity to make it safe, versus a short, where we dropped the screwdriver into the pump circuitry. Which then that was a big mess, because then that sends a surge of current back through all the other stuff, and we had to go back through and figure out what did we blow, what didn't we blow. We had fuses all over the place that we popped because of this. Luckily, we didn't damage any other components, but we had a lot of fuses we had to go replace. And trying to find them all was a pain in the butt. That tool sat down for weeks while we traced out the circuitry.
Your boss was super happy.
Oh yeah, he was super happy. Super happy. It was and of course, and it didn't help that it was the top tool in the plant at that time. So yeah, it was not fun. So luckily, I wasn't me that dropped it, so I wasn't too worried about that.
I mean,
And unfortunately, there was that. It's because there was a lot of cover your butt type of things. You know, it was very documented who was doing what, and if it was honest, and if it was an honest accident, the thing was you just had to fess up to it. Because if you try to hide it, then you would get in trouble. Especially in the corporate world. If you're just open with things, it usually goes a lot easier. Yeah, you may still get into some trouble, but you're not going to get into nearly as much trouble as if you try to cover it up. It's crazy. People think it's always better to not tell, not get in trouble. My kids still think that. They still think it's better to try and cover up their lies instead of just flat out telling us. And we've showed them and we've proved to them. Yeah, we were pissed that they did something, but because they came and told us, they may have gotten grounded, but it might have been grounded just for the night versus where they were adamant and kept changing their story that they didn't do something. They were grounded for a week. So hopefully with my kids that we've at least tried to establish that, be honest about your mistakes, especially if they cause damage to tools. And again, it's not worth your life or your job to try and hide stuff, especially when safety is involved. If anything with safety gets brought up, it's better to be honest about it. It's so much better to be honest with it. Anyway, that's where we'll go for right now. Let's go ahead and take our 5-minute break. And then when we come back, we have just a few more terms I want to cover, and then we'll get into the math.